Dear students, here in this lecture we will consider about the rotational energy levels in the case of molecules. As the molecular energy state arises from the rotation of the molecule as well as from the vibration of its atom. And so here first we will consider here how the rotation of the molecule due to the rotation of molecule, how we have the rotational energy levels. So, in the case of molecules, we have a rotational states, and then we have vibrational states, and we have electronic states. Okay, that's why the spectrum of the molecule arises due to the rotational states, due to the rotation of molecules, and due to the vibration of atoms in the case of molecules, and due to the electronic energy levels. So combinedly, in the case of molecules, we have the rotational spectra, vibrational spectra, and electronic spectra. The rotational states, which are separated by quite small energy level intervals, like their separation distance in the case of rotational state is 10 to the power minus 3 electron volt. So this is the this spectra arises from the transition between these rotational energy states. Okay, and their spectrum, corresponding spectrum, lies in the microwave region, and spectrum is in the microwave region. And now then we comes to the vibrational state. The vibrational state are separated by a somewhat larger energy interval as compared to the rotational state, and the interval between the energy states in the case of vibrational energy level is uh, typically of 0.1 electron volt. Okay, and then vibrational spectra lies in the infrared region. It's in the infrared region, and because their corresponding wavelength is 1 micrometer to 0.1 millimeter, 1 micrometer to 0.1 millimeter, while in the case of a rotational state, the wavelength of in the wavelength here in the case of vibrational state is 0. Its range is 0.1 millimeter to 1 centimeter. Now then we comes to the electronic state, the molecular electronic states. Here these are at highest, their separation between the energy level is higher than the vibrational and rotational states, and these separation between these energy levels is of several electron volt, can be of several electron volt, and the corresponding spectra we get is in the visible and ultraviolet region. Okay, so in the molecule we can get the spectrum. We have the rotational state, we have the vibrational state, and we have the electronic state. That's why correspondingly its spectrum is contain the rotational energy level, vibrational energy level, and electronic energy level. So here first we will consider the case of rotational state or rotational energy levels. So first we are here going to consider rotational energy levels. Okay, for simplicity, here we consider a diatomic molecule. So diatomic molecule which is considered which is consist of only the two atoms of mass m1 and m2. Now, how we can realize the diatomic molecule? So here we consider it like this one. So we have the two atom of mass like M1. This is the atom of mass M1, and then we have the other atom of mass M2 separated by a distance R, and here this one is the central axis, so through which this is also called as the axis of rotation, and both masses are rotating about their common center of mass. So we can say this one is the center of mass. Center of mass of two atoms M1 and M2. So they are combinedly rotating about their common center of mass. Okay, and this one is the axis of rotation. Now, here we consider R distance of R1 is of mass M1 and R2 is the distance of mass M2 from the center of mass, and the distance between the two masses can be written as R. So here we have some mathematics. So the R, which is here, you can see it's a combination of R1 plus R2, and here M1 R1 will be equals to M2 R2. Okay, so and both masses here, the R1 and R2 are the distance of atom 1 and M2 atom 2 respectively from their center of mass, and so from the definition of the center mass we can have M1 R1 is equals to M2 R2. So this is our equation 1. So here we can find out the value of R1. R1 will be equals to M2 divided by M1 into R2. So this is our equation number 2. So again, by putting the value of this R1 into equation 1, so here using equation 2 in equation 1, we get R is equals to M2 divided by M1 into R2 plus R2. So from here we can get the value like M2 divided by M1 plus 1. Here R2 will be the common, and so this will be equals to M2 plus M1 divided by M1 into R2. So here we can write the R2 in term of R. So we can write this equation. So here it is equals to R. So it is R2 will be equals to M1 over M1 plus M2 into R. So this is our equation 3. So in the same way we can write the R1 in the form of R. So we can write it by putting equation 3 in equation 1. So from there we can get R1 will be equals to M2 divided by M1 plus M2 into R. So this is our equation number 4. So now the moment of inertia of whole system, we can write the moment of inertia of diatomic molecule as I. Inertia can be represented by I. So it's a combination of I1 plus I2. So as we know that inertia is equals to mr square. So the combined inertia, we can write it like I is equals to m1 r1 square, that is inertia of atom 1, plus m2 r2 square, that is the inertia of atom 2. So this one is our equation 5. So now using the equation 3 and equation 4 in equation 5. So by putting the value, so by putting equation 3 and equation 4 in equation 5, we get the value of inertia in term of mass. So it will be equals to m1 into m2 divided by m1 plus m2 into r square plus m2 into m1 over m1 plus m2 into r square. So from here we can take the common term as m1 m2 divided by m1 plus m2 into r square m2 square, here r square plus m2 m1 square divided by m1 plus m2 whole square, here is also whole square into r square. So here we can take the common term like m1 m2 divided by m1 plus m2 into r square. So and here we have m1 plus m2 divided by m1 plus m2. So from here we can get the inertia in term of r as well. So inertia in term of r, it is equals to we can write it m1 m2 divided by m1 plus m2 into r square. So now we comes to the, as our inertia is here, again I can write it like m1 m2 divided by m1 plus m2 r square. So this is our inertia. Now what is m1 and m2? So here I can write it like this one. So mu is equals to, I can write it m1 m2 divided by m1 plus m2. So I will be equals to mu r square. So now here this is called as reduced mass. So this is the reduced mass. Now what is the reduced mass? Reduced mass is that instead of two bodies, two atoms, that is of mass m1 and m2 rotating about their common center of mass, so instead of two masses we can take the one mass, which is that has the combined mass m1 m2 divided by m1 plus m2 rotating about the center of mass. So this is called as the reduced mass. That is, now instead of two body system we have only the one body which is having the reduced mass. So this is m1, this term m1 m2 divided by m1 plus m2 is called as reduced mass. So this is our equation number 6. Now the rotational kinetic energy, we know that we can write the kinetic energy rotational. Here the kinetic energy is the rotational kinetic energy of system. So we can write it like E is equals to 1 by 2 I omega square. That is, I is the inertia and omega square is the angular frequency. So this is the energy of rotating molecule. Energy of rotating molecule, that is rotating about a common center of mass. Rotating molecule having the angular frequency omega. So here I can again draw it here. So this is the body of mass m1, and then I have the body of mass m2, that is rotating about their common center of mass, and this one is the axis of rotation, and it has the angular frequency omega. So omega is the angular frequency of rotation. So we also know from the angular momentum L will be equals to L is equals to I omega, and from here we can have the value of omega is equals to L over I. So this is our equation number 7. So we can use this equation number this equation. So this is our equation 7, and this one is our equation number 8. So we can use our equation 8 into the kinetic energy equation. So putting this value of omega, so putting the value of omega, we can have the energy which is equals to 1 by 2 I omega square. So when we put the value of omega is equals to 1 by 2 I into L square over I square. So this will be equals to 1 by 2 L square over I. So this is our equation 9. So it represents the energy of rotating molecule. So here I can use the subscript J for different energy level, and so now the quantum mechanically we know that the angular momentum of the system about an axis can be given by, like, its magnitude is always equals to L is equals to, here instead of L I will use the J into J plus 1 underscore H cut. So this is our equation 10. As we know that usually in the case of orbital motion, the angular momentum magnitude is L into L plus 1 into underscore H cut. Here L is the orbital quantum number, but here we are dealing with the rotational motion of a rotating molecule. So here J represents the rotational quantum number instead of orbital quantum number. So it is rotational quantum number. So this rotational quantum number, and so J can have the value of 0, 1, 2, so on. So by using this value of L, uh, which is given in the equation 10, by putting it in the equation 9, we have the energy value. It will be equals to, which is equals to L square over 2I. So this will be equals to, we can write it like uh, J into J plus 1, J into J plus 1 H cut square over 2I. So this is our required rotational state, that is, it represents the rotational energy levels. So these are the rotational energy levels. Okay, for when we put the value of J is equals to 0, then Ej, which is equals to E naught, will be also be equals to 0. And similarly, by putting J is equals to 1, then E1 will be equals to 2 H cut square over I. Okay, and similarly when over 2I, and in the similarly when we put like J is equals to 2, and then E 2 will be equals to uh, 6 h square over 2I. So in the same way we can get the different energy level, and I can draw it like for here J is equals to 1, it is E naught, and the same way for J is equals to 1, it is E1 is equals to 2h square over 2I, and then for J is equals to 2, E2 is equals to 6h square over 2I, and for J is equals to 3, it is equals to E3 will be equals to 12h square over 2I, and in the same way we can get the J is equals to 4, it will be correspondingly energy level will be equals to 20h square over 2I. So we can get the different energy levels for the different rotational energy level. Okay, and now we comes to the selection rules. That what are the selection rules? As we know that all energy levels are not allowed. So what are the energy levels which makes the rotational spectra? Now we will explain the rotational spectra. Rotational spectra. Rotational spectra arise from the transition between rotational state. That is, rotational spectra arise from the transition between rotational states. So just like even like the molecule with the permanent dipole moment, not all transitions are possible between the rotational states, which involves the radiation. As in the case of atomic spectra, certain selection rules summarize the condition for radiative transition between the two rotational states to be the possible. So here we have some selection rules uh, for the rotational spectra. So what is the selection rule? The selection rule for the possible transition is del J is equals to plus minus 1, as we already know that J is the rotational quantum number. So like we have J is equals to 0, and here we have, first we need to draw here, this represents the energy AJ, energy scales, and so J is equals to 0 corresponds to the first energy level, and then we have J is equals to 1, J is equals to 2, and then we have J is equals to 3, and J is equals to 4. So these corresponds to the different value of the J. We have the corresponding different energy states, as we have already discussed that energy levels are equivalent to EJ is equals to J into J plus 1 h square over 2I. So this represents the rotational energy level. So these are the rotational energy level. So according to this selection rule, the transitions which are possible between the, say, for delta J from J is equals to 0 to J is equals to 1, because here this it obey this rule. In the same way, from J is equals to 1 to J2, del J difference between the two J is 1. Again, in the same way, from J to J3, J3 to J4. So all these are the possible transition. In the same way, we can have from J4 to J3, and so J3 to J2, J2 to J1, and J1 to J0. So all these are the possible transition according to this selection rule, delta J is equals to plus minus 1. But in practice, the rotational spectra are always obtained in the absorption. That is, it is the absorption spectra. So each transition that is obtained is always from initial state to the next higher state of quantum number j plus 1. So like in the case of rigid diatomic molecules, and so it is always we have the absorption spectra in practice, so there is no emission spectra. So we don't have these spectral line from higher to lower energy level. We have only the transitions which are possible transition are always from lower to higher energy states. Okay. So because as the photon atom absorb the energy, it goes to such into the rotation. As a result, there is the transition from in between the rotational energy level, and so this spectrum is always absorption spectrum. So this is always absorption spectrum. Whenever molecule absorb the energy, absorb the photon, and then it's set into the its atom set into the rotational motion. As a result, we get the rotational energy levels and the rotational motion. So now we go to the frequency of absorbed photon, which is the frequency of different lines in the absorption spectrum. So here we know that spectrum correspond to the each transition there is the separate line which represents the transition from lower level to higher energy level, from j is equal to 0 to j is equals to 1, and then j is equals to 1 to j is equals to 2, and so in this way from lower j to higher j, that is j plus 1. So correspondingly we get the different spectral line. Now we need to know that what is the frequency of this spectral line. So now we comes to the frequency of absorbed photon. What should be the frequency of absorbed photon, as a result of which we get the absorption spectrum. So as it is the absorption spectrum, so it is always from j to j plus 1. Okay, where so frequency of the line from j to j1 is always equals to del E over H, and so it can be equals to E j plus 1 minus Ej. That is difference between the higher energy level to lower energy level over H, or we can write the H mu j2 j plus 1 is equals to E j plus 1 minus Ej. We already know the value of Ej and Ej1, so from there we can write H mu will be equals to, from j to j plus 1 will be equals to j plus 1 into j plus 1 plus 1 over 2I minus j into j plus 1. So here is h square into the over 2I. As we know that I is the inertia and it is equals to mu r square, so we can write here h mu is equals to j plus 1 into j plus 1 plus 1 h square over 2 mu r square minus j into j plus 1 over h square divided by 2 mu r square. Now we can further simplify it. So we can further simplify it as h mu is equals to j plus 1 into h square over 2 mu r square as a common factor, and then we have j plus 2 minus j here. So next further simplification lead us to the h mu is equals to j plus 1 h square over 2 mu r square into here. We can cancel out the j and we have 2. So again we can cancel out the 2 as well and we get j plus 1 h square over mu r square. So here h you know that it's equals to h over 2 pi, and h square will be equals to h square over 4 pi square. So putting the value of h square into the above equation, we will get the equation will become h mu is equals to j plus 1 h square over 4 pi square into mu r square, and it will be equals to j plus 1 into h dot h over 4 pi square into mu r square. Here we cancel out 1h with this 1h and we can further simplify it and we can write it like this one. Now the mu will be equals to j plus 1 into h divided by now we can split the 4 pi square into 2 pi into 2 mu pi r square. Okay, and here further we can convert the h over 2 pi into here that is h over 2 pi. We can write it like the h cut. So now we can simplify it. Mu is equals to j plus 1 into h cut divided by 2 pi mu r square. Now again we can replace the I is equals to mu r square, and then equation becomes mu is equals to j plus 1 h square divided by 2 pi I. So this is the frequency of the rotational spectra. So this is our desired equation, and this equation gives us the rotational spectra, frequency for the rotational spectra, spectral line, frequency of rotational spectral lines. Okay, so this is our desired equation. And so for example we can write it for, let's suppose as our equation is, again I can write the equation here, h cut over 2 pi I into j plus 1. So for j is equals to 0, we have mu as is equals to j plus 1 to j as in j2. Sorry, our equation is like this one, from j to j plus 1 is equals to, it will be equals to, for j is equals to 0, it is equals to h cut over 2 pi I, which is equals to mu naught. Okay, and so when from view mu 1 to 2, it will be equals to 2 mu naught. Okay, and then from j is equals to 2, so this corresponds to j is equals to 1. For j is equals to 2, mu will be equals to 2 to 3. J is equals to 2 to j is equals to 3 is equals to 3 mu naught. And in the same way, for j is equals to 3, we have the frequency from third energy level to 4. That is transition from 3 to 4 to next higher energy level. This corresponding frequency will be equals to 4 mu naught. So here you can see that for j is equals to 0, we have the corresponding frequency, that is from j to j plus 1, that is from 0 to first energy level. So 0 to first energy level, here we can write it, that is it corresponds to mu from j is equals to 0 to j plus 1. Again we put j is equal to 0, it's equals to v plus 1 is equals to mu naught. So from 0 energy level to 1 energy level, the corresponding frequency for this spectral line is mu naught. And for first energy level to second energy level transition, the corresponding frequency of this spectral line is 2 mu naught. And for the transition from second to third energy level, it is 3 mu naught. And in the same way, for the transition from third to fourth energy level, the corresponding frequency of the spectral line is the 4 mu naught. So there is always transition from lower energy level to higher energy level, that is from 1 to 2, 2 to 3, 3 to 4. So this is absorption spectrum. So as they are at equal distance, so we can say that the rotational spectra of the diatomic molecule consist of spectral line which are equally spaced, as we can write. So if we draw a spectral line, so the spectral line, this is a frequency mu naught. Here we can draw of lines of frequency 2 mu naught, and this corresponds to 3 mu naught, and this corresponds to 4 mu naught, this corresponds to 5 mu naught. So all spectral line lies at equal distance, all are equally spaced. So this was all about the rotational energy levels and rotational spectra of diatomic molecule. Thanks for watching. For more videos, please subscribe our channel.